Welcome to the Copper Spice YouTube channel, and thanks for joining us. In this video, we are going to show multi-threaded examples to demonstrate a more reliable approach. Mutex plus lock equals CsLibGuarded. In our last few videos, we have talked about the C++ memory model, atomic data types, and how to use a mutex. You may want to watch these before proceeding with this video. There is a new question we want to consider. Is a low-level mutex the best solution for protecting data from race conditions in a multi-threaded application? In this video, we are going to show mostly examples. Our premise is that we should be using a higher-level abstraction, which will increase the clarity of the code and eliminate many of the common multi-threading errors. The C++ committee did their homework, and they realized the language should have a threading library. By adding it to the standard and not depending on a third-party library, they can ensure the functionality was in alignment with the new memory model. We believe it was a good decision to add the memory model and STD mutex at the same time. This is one of the reasons C++11 was such a big deal, especially for multi-threaded applications. Implementing a mutex class requires platform-specific code, and part of the point of having a standard is to provide consistency and reliability. There is nothing wrong with STD mutex, but what does it mean to lock a mutex? How does this lock indicate that it is protecting some shared data? This is sort of like having a padlock located next to your front door, then trusting strangers to respect when the lock is engaged. Oh, please do not enter my house. This is a bit awkward or silly. The lock should be on the door itself and physically prevent someone from opening your door. The STD mutex class has the same problem as our padlock. It is no more than a request which you hope other programmers will honor. This is C++, and we can create data types by writing a new class. This will allow us to bridge or unite the data, the mutex, and the lock.
Before we show our new data type, let's begin by looking at a typical example of code which uses the STD mutex class and then rewrite it. We are declaring a class named Ginger, which contains two methods and one piece of data. Since this class will be used in a multi-threaded application, we need to add a mutex to allow both methods to protect mdata and not have any race conditions. The mutex is mutable, so the getData method can be const qualified. In the implementation for this method, we will need to lock the mutex, and this requires write access to m_mutex. During a code review of this class, there is no indication that the mutex is intended to protect the variable m_data. It might be obvious in this case, since this is a simple and very short class. In a larger class which is managing multiple pieces of data simultaneously, it would be much harder to reason about the code, and you can potentially miss a race condition. The implementation of these two methods is pretty short. In both cases, we acquire a lock on the mutex and then do something. In addValue, we add the value of the passed parameter to mdata, and for getData, we simply return the current value of mdata. Even with these simple methods, there are several potential threading issues you must be aware of. Both methods need to lock the correct mutex. This is the padlock designed to protect the data. Locking the mutex is the way to ensure the data is not accessed by another thread while this method is using it. If the wrong mutex is locked or the lock is missing, you now have a race condition. According to the C++ standard, a race condition is undefined behavior, and your code is incorrect. Easy examples like this one are typically fine, But it can get complicated and things go wrong much faster than most programmers realize. We want to rewrite our first example and use a custom data type which encapsulates the data, the mutex, and the lock. This example shows how to use the most basic class provided in the CsLibGuarded library. All of the classes in this library are templates, and it is a header-only library. It is open source with a BSD license. Full source code is available on GitHub in the CopperSpice project. Now, instead of having a mutex and a separate data member, they are combined into one variable. By looking at the declaration for mdata, you cannot see the mutex, which is the point. The mutex and the lock are declared and managed by the LRGuarded class. The template parameter is simply the data type of your data. In this example, we are storing an integer, just as we did in the first example. In our original example, the first line of code in add value locked the std mutex. In this code, the first line calls the lock method in LRGuarded, and this returns a smart pointer to the physical data. When pointer goes out of scope at the end of this method, or by assigning null PTR to this variable, the lock on the mutex will be released. The LRGuarded class is responsible for managing the mutex and the lock. The only way to change or even access the data is by obtaining a pointer from CsLibGuarded. With this design, the mutex and the data it is guarding are now connected. It is impossible for the programmer to forget to lock the mutex because the data is encapsulated and cannot be accessed without calling the lock method. There is no chance for a race condition to exist, and a code review will be much easier.
In the prior example, we were using the LRGuarded class, which is a better choice when every access to the data is a potential write. In this third example, we are swapping it out for the LRGuarded class, which can be faster when there are mostly read operations. In this class declaration, we are removing the mutable keyword for mdata. This is an excellent change since marking a data member as mutable often indicates an improperly designed class and raises questions in a code review. The implementation for the add value method does not need to change when using the LRGuarded class. Our getData method is a reader and does not need exclusive access to the shared data. So why not take advantage of this and change the way we retrieve the pointer to the data? We use LockShared instead of lock. The LockShared method returns a const smart pointer, which means the pointer cannot be used to modify the data. Trying to change the value of the data with a const pointer is actually a compile error. It is also a compile error to call the lock method in a const qualified method, since lock does not return a const pointer. If we had used std shared mutex rather than std mutex in the very first example, we would have the same runtime performance as we have in this example. However, the two compile time checks would not happen since the std mutex classes have no information about the data.
There is another class in CsLibGuarded we should consider. This example uses the LRGuarded class, which maintains two copies of the data in Ginger. One copy of the guarded data is used exclusively by the current writer. All readers can simultaneously access the other copy of the guarded data. With this design, readers never need to wait for a write operation to complete. The trade-off for allowing readers to proceed without being blocked is that space must be allocated for two copies of the data. If the data you are storing is very large, this class may not be the best option. For something like an integer which only takes up a few bytes, this is not a significant concern. Any modification to the data actually requires changing both copies of the data. All of this is handled by the LRGuarded class. Having the user obtain a lock in addValue is not reliable and would end up blocking. The implementation for addValue is simply a lambda expression which does something. The evaluation of any lambda expression produces what is called a closure, and this is what is passed to the modify method in the LRGuarded class. The modify method is responsible for invoking the closure and correctly guarding the data. What is really interesting is that the modify method uses the same exact closure to update both copies of the data. It is rather stunning that the implementation of the modify method only requires C++11 functionality. The getData method implementation uses the same code as our previous example. In our final example, we are presenting the use case which was the inspiration for developing CsLibGuarded. Our CS signal library provides the ability to connect senders and receivers together in a signal slot relationship. Consider the example where the sender is a push button and the receiver is a window. We might want to establish a connection, so when the push button is pressed, the window is closed. For proper cleanup, there needs to be some housekeeping in the CS signal library. Senders need to maintain information about who should receive notices, and this information is placed in a receiver list. The receivers need to track their senders, and these are saved in a sender list. This housekeeping can get messy, but this is a common situation. The problem happens when the window is closed. The destructors for both the push button and the window will be called. During this process, the sender and receiver objects both need to update their own containers. At the same time, they each need to inform the other object to update their list. There is a decent chance both destructors may be running at the same time. Depending on how this code is written, you will either have a race condition or a deadlock. We lucked out and discovered we had both problems.
Solving this problem correctly requires more complexity than simply guarding the two containers with a mutex. You also cannot add a mutex for each element in the sender list and the receiver list. The solution requires the implementation of an RCU list, which stands for Read, Copy, Update. The design actually involves storing the data in a linked list and maintaining multiple atomic pointers. Once this class was in place in CsLibGuarded, updating the destructors was easy. All the heavy lifting is done in the RCU list class. We have posted a small PDF which shows the relevant signal destructor code before and after we switch to using this solution. We have verified our code with Thread Sanitizer and found no race conditions or deadlocks.
For more information about the CopperSpice project, please visit our website at www.copperspice.com.
Thanks for watching. We hope you found the content of value. If you have any questions or feedback, feel free to leave a comment on this video or send us an email.
Please make sure you subscribe to our YouTube channel and come back in a few weeks for our next video.